uh, this is my title. And
Yes,
okay,
yes, Moshe. Oh,
Ex
okay.
excellent. Thank you very much, Vasily. Thank you, graduate student. This is the graduate seminar. I'm very happy to address you. I think those of you who are first year, this will be my second address, and those of you who are not first have seen this address. I would like to tell you a little bit story. Most of you were not born when this story happened. And a story of cold fusion. You may have heard of cold fusion. I would recommend that you maybe Google it. And the question is, what have we learned? This was one of the worst scientific blunder. And what have we, and in particular the White House, learned? Uh, as you may know, I am working in Avery Point. It's one of the campuses of the University of Connecticut out there by the New London Harbor. Beautiful campus, a great place to just have time to think, you know. Most of the time we run around catching our tail, but while we're here, we have time to sit down and think. We're away from the main, how should we say, rush of the main campus. Cold fusion. Cold fusion was announced on March 23rd, 1989, by what the Time magazine called obscure chemists that stir excitement and outrage in the scientific world. Appropriately so, Time asked, is it fusion or illusion? The fusion was supposed to happen. I assume you see my cursor, right? Okay.
I could see it. I am not
Yeah.
sure about all audience. I could see it.
Yeah, I think if you see, everybody sees. So in this little flask over here, in this jar, just the size of a human hand, this is the jar. They have claimed to create cold fusion. Um, let's remember the time. This is May 1989 in Beijing. The angry students are in Tiananmen Square. But most important, a day after the announcement of cold fusion, on March 23rd, the Exxon Valdez ran aground and spilled into the Prince William Sound, probably the largest amount of oil spilled into any waters. Clearly, energy, environment is on the front page. Everybody's asking, where are we going to get our energy and how are we going to protect our planet? Naturally, when people come with a solution, infinite amount of energy for very cheap, the excitement is brewing, and as you see, it will. What did they actually claim to do? They claim to have a beaker full of heavy water. So this is water which is, instead of hydrogen H2O, we make deuterium, which is an isotope of hydrogen, one neutron, one proton. You drop a little bit of lithium into this heavy water, you create something which is called lithium hydroxide, lithium OH, and in this case, it will OD. In this dual electrolysis, you have one cathode made out of palladium. Palladium is a key ingredient. You could also have titanium. And the other one is just some noble material, and with platinum will do. You put 10 volt across the battery, plus 10 volt on the anode, ground, or minus 10 on on the cathode, and you create the phenomena called electrolysis. In this electrolysis, deuterium get implanted or loaded into the palladium. The claim is that as the deuterium was loaded into the palladium, new phenomena previously unobserved took place, nuclear reaction took place, it created heat which would raise the temperature of the solution. So if you do your thermodynamic right, you know how much energy you put in. How much energy you put in, it's 10 volts. The current or the electrolysis could be 0.1 ampere, 10 times 0.1 is 1 watt. 1 watt comes in, you do your thermodynamic correctly, and you claim that 4 watts came out. Now, this is like a return of 3 on 1. That's a pretty good return. You're producing enormous amount of energy, a factor of 4 more than what you put in. All of this in a little jar. Clearly, if correct, a revolution. Hallelujah. We have free energy. No need for Exxon Valdez. No need for oil. The future is here. The Messiah came, not a donkey, but in a jar. A lot of books were written on this period. John Hughes Zenger, who was the chairman of a review committee, Energy Research Advisory Board Committee, wrote his own book with the title Cold Fusion, the Scientific Fiasco of the Century. He's modest. It's probably a scientific fiasco ever since Aristotle invented logic. Another book was written, I'm just showing to you three very central books. Gary Taub, one of the best science writers that I know, spent 6 months writing this book, and he's calling it The Short Life and Weird Times on Cold Fusion. Some of you may want to read actually Gary Taub's books on physics. He wrote a beautiful book on Mr. Carl Rubia, got the Nobel Prize in 1982 for the discovery of the gauge boson, the Z particle. He had 2 events. This is one of them. This is 50% of a Nobel Prize, this picture. Another event. And Gary Taub wrote a book about him. I was already familiar with Gary Taub, but through Cold Fusion, I got to know him even better. Another book was written by a member of the American Physical Society, Robert Park, sadly just died a year ago, April 2020. And he calls his book Voodoo Science, the road from foolishness to fraud. Foolishness to fraud. Yes, there was some fraud, but that's another story about cold fusion. So, what is being claimed? If deuterium does a nuclear fusion, 50% of the time a neutron will be emitted. It must be emitted by the laws of quantum mechanics. And energy will be produced. 50% of the time it must emit proton, and triton will have to be left behind. Fusion results will have to be, the telltale of fusion will have to be there. A tiny amount, a very small branching ratio, goes directly to making helium plus a very high energy photon. Pons and Fleischmann claimed A, we observed excess heat, 1 watt in, 4 watt out. Originally, they claimed to observe helium-4. Later, it was retracted. And they claimed to measure neutron. To their defense, they noticed that the amount of neutron that they measure is 100 million, 10 to the 8 below what is expected. If all the neutron that expected were to be emitted, they will be dead on the spot. It turns out to be that these subjects have a history. In the 1920s, Panis and Peters thought that they transmuted hydrogen into helium. They didn't know about deuterium. Quantum mechanics was just introduced. They were chemists, didn't know about. Transmutation of the element has been discovered by Rutherford in 1911. It was a big thing to do. Why was it important to transmute hydrogen to helium? Transatlantic transportation was done by Zeppelin, you know, the Goodyear balloon, the football thing that flies in the air. In the United States, where we have the world supply of helium, the Zeppelin were filled with helium. In Europe, they didn't have helium. They filled it with hydrogen. Major explosion took place. You may have seen the Hindenburg that exploded in New Jersey right before the war in the 1930s. So getting helium to Europe was a major thing. Baneth and Peters, the honest chemists, they found the mistake and the illusion was over. The second introduction is something called muon catalyzed fusion. This is real science. In muon catalyzed fusion, what's happening is the following. The muon is the cousin of the electron. It's the same electron, it's a lepton. It's 200 times more massive. The muon can replace the electron in the hydrogen. So if we make muonic atom, so here is, for example, tritium, that's hydrogen with 2 neutrons. This is the isotope of hydrogen called tritium. If a muon rotates around it just like an electron, the K shell radius is 200 times smaller. The Bohr hydrogen is 1 over the mass, the radius 1 over the mass. So then if a triton and deuterium get together into a molecule which is bound by a muon, the deuterium and the tritium are pushed together closer and a nuclear reaction emerges. In this nuclear reaction, we produce helium plus a neutron. So in order to measure this muon catalyzed fusion, we need to measure the neutron. It turns out to be that once you produce helium, the muon will go and catch another molecule and will do this cycle. If the muon lives forever, we will have free energy because one muon can do as many reactions as we want, as long as we don't lose the muon. How can we lose the muon? The helium atom can make a muonic atom, and that's it. The muon is taken out of the cycle. A very good physicist by the same Steve Jones made a name for himself with muon catalyzed fusion. You may recall, in order to measure muon catalyzed fusion, you need to measure the neutrons that are coming out. He had developed a very good neutron spectrometer. He knew what he was doing. He measured neutron, and he measured that muon can be used 150 times to create that fusion. Well, it turns out that to produce one muon, the accelerator has to give you 10 GeV. 150 fusion give you only 2.7 GeV. So in order to break even, but now we're talking about physics break even, the amount of energy that it takes you to make a muon and the amount of energy that you get out of it, they're about a factor of 4 too small to break even. Now, we all know that the energy that makes the muon is not the energy of the facility. The facility has coffee maker, elevator, pumps, magnets. All of these take a lot of energy that we need to give to the facility. So in order for the facility to be energy producing, we need 10,000 muon catalyzed fusion. We are about a factor of 100 off. No hope for muon catalyzed fusion being our energy source. However, what we see is Steve Jones actually developed a neutron detector. We will come back to this. Another phenomenon which we need to discuss is sonoluminescence. In sonoluminescence, we have water with some noble gas, helium. We pump in here acoustic energy. The bubble oscillates, and when the bubble oscillates, it luminesces. It gives us blue light. It's a beautiful phenomenon. So here is the sonoluminescent cell, piezoelectric element, piezoelectric element, pump acoustic energy, and we get blue light. Acoustic energy is 10 to the minus 11 eV. blue light is 3 eV. We have 11 orders of magnitude different between input and output. In cold fusion, we have 10 volt EV energy. We get out of it MeV, 6 orders of magnitude. So these sonoluminescence confuse some people. One of them is a Nobel laureate, Julian Schwinger, and said, well, here we have 11 orders of magnitude different, cold fusion is possible. The truth is that in order to emit blue light, it's a black body, this bubble has to be at 10,000 degrees. Room temperature is 300 degrees. So all we have to do is compress the bubble 3 times. 3 to the power 3 is about 30. 30 times 300 is 10,000. And that's how we produce light. Nothing to do with anything exotic. Coming back to cold fusion. So we have scientists telling us, I put 10 volts into this electrolysis cell, I get heat, I get energy, I measure helium, later detracted, and I measure neutron, 8 orders of magnitude different. And that was March 23rd, by the way. They submitted the paper on March 11. 11 days after they was submitted the paper, it was accepted. I know of no paper that was accepted in 11 days. A day later, they have a press report. On April 12th, the paper appeared in publication. We are moving in a speed which is unbelievable, unheard of in the history of science. And then come the months of April. April madness, not March madness, April madness. And let's just look on one corner of the universe. Boston, New England, Boston, Massachusetts, the mecca of higher education, MIT, Harvard, our best. At MIT, Peter Hagelstein came up with a theory for cold fusion. Consequently, the professor of MIT, John Deutsch, announced on the front page of the New York Times that MIT will apply for a patent on cold fusion, the provost of MIT. John Deutsch was very well connected, later became the head of the CIA. When John Deutsch talked, people in Washington listened. Okay? MIT got into a furor about whether they should give Peter Hagelstein tenure. That's later, in December 1989. The physicists shouted bloody murder. Then there was a provost, and the provost was, by the way, a chemist, and there was the Department of Engineering, where Peter Hagelstein was there. Never mind Peter Hagelstein. But you see, MIT is announcing we are going to apply for a patent on cold fusion mere 3 weeks after the announcement. Why did John Deutsch spoke so eloquently? Julian Schwinger on the other side of Massachusetts Avenue in Harvard, 1965 Nobel Prize, had a theory to explain cold fusion, just like Peter Hagelstein. Julian Schwinger submitted a paper to the APS. It was rejected. He was so pissed, he was so furious, he resigned from the American Physical Society when his paper was rejected. In the same university, probably across the hall, was Norman Ramsey, another Nobel laureate. And he will play a major role later. He also said, oh yeah, it is possible. So here we are. In April, confirmation came from Texas A&M. Georgia Tech claimed to see neutron. Los Alamos, our revered national lab. Confirmation came from Italy, Japan, USSR. April madness. During that time, April 1 to April 2, oh, sorry, I'm ahead of myself. April 26, 1 month, April 23rd, March 23rd is when we had the announcement in a press conference. And 1 month later, Jones and Fleischman appear in front of Congress in a hearing of the Committee on Technology, requesting $25 million from Congress. They're going directly to Congress to get funding for their science. When I ask for money, I don't ask for $25 million. But when I ask for money, I have to go through a review process. In fact, I am now being reviewed right now, and I have to wait 6 months. Here they are. Utah and BYU both appeared in front of Congress. BYU is Steve Jones and Pons and Fleischman, the promoter of cold fusion, asking Congress to give money. They gave a passionate speech to Congress. Says, look, here we in America, we are the one who studied microwave interaction, microwave radiation, blah, blah, blah. Microwave ovens are made in Japan. United States cannot lose on this. United States must have priority to develop cold fusion. It was a passionate, very eloquent, very convincing. And you're not a scientist. What can you say? John Deutsch is telling me it's correct. During all of this April madness, from April 1 to April 21, meanwhile, 3 weeks at Yale, we did our study. Moshe Gai, a Yale physicist and a member of the Yale Brookhaven collaboration. This is this Time magazine that I showed you. Here I am. They asked me to decorate myself, put a tie. I begged them, why don't we put some student in the picture? They finally allowed me to choose one. So I chose Jiping Chang, a very decorated undergraduate student, received the award of the American Association for Women in Science, best graduate student, and then another award from the American Physical Society for the best PhD thesis that she wrote with me on another subject, on real physics, on astrophysics. Here is our experiment, okay? This is an experiment. You will recognize those truncated hexagon vector. 3 weeks, there was no evidence in cold fusion. Okay, and just to give you a little bit of a taste of the madness of April, one day I received this letter from somebody from Iowa. Just a moment. Here is this letter. It is on a page which is 1.5 feet long by 11. And in this letter, he sent me a name tag. And I look at this and one boom guy. What is this? Guy, I have to explain to you. My name is Guy, is a Hebrew word. So when I had to choose spelling, I didn't want to have a word for my name. It's enough that in Hebrew, Guy is a word. I didn't want my English name to be a word. I didn't choose G-U-Y. I chose the spelling G-A-I. Unbeknownst to me, I chose my name to be a word in the Chinese language. I won't tell you what it means, but next time when you go to a Chinese dinner, look up in the restaurant menu and you'll see Mugu Gai Pan. It's the same guy. So this person, I would not reveal his name, sent me a letter from Iowa, says, I made for you a name tag. And I look at it and says, Steve, what is this all about? You call me one doom guy. What does it mean? It says, Moshe, it's not one doom guy. He is calling you one dumb guy. Imagine a person actually went and created this name tag for me. It's still in its original packaging. The letter, by the way, I have a file called Cold Fusion Nuts. I receive letter. This is just one of them. Daily letter. The world was in a major state of excitement, and how dare I am say that it is wrong. Another thing happened during that April. On April 21st at 7:30 in the morning, my boss at Yale, D. Alan Bromley, received a call from President George Bush. Alan Bromley told me I was in the shower, so I'm holding the phone, all dripping, and he was a good friend of George Bush. And George Bush says, I want you to come to Washington and be my science advisor. Okay, April 21st, my boss at Yale became the science advisor to George Bush. Here he is, Alan Bromley, being sworn in by Dan Quayle, the Bible held by his wife, Pat. President Bush looks, and all this is under the looking eyes of George Washington. Alan Bromley, when he came 4 years later from Washington back to Yale, he wrote a book, The President's Scientist, The Reminiscence of the Science Advisor. This book he wrote as something very important at Yale. They have a Silliman lecture, and the Silliman lecture invite a distinguished scientist to give lectures, and then they publish the book of their lecture. So that's the book that is, mind you, another very important Silliman lecture was given by Hubble in 1936, and that is the famous book, The Realm of the Nebula. 1936, Hubble wrote this book. It will be 1993 when Alan came back from Washington. He's writing the book where he tells the story of the science advisor. And I must admit, 2 weeks before April 21st, I knew something happened. Alan came and says, I gotta go to LaGuardia. I'll be back in the evening. I have an important meeting in the White House. Well, we are in the middle of this most important experiment, and he goes to the White House. Something must be very big. As Alan writes in his book, on page 16, On the Way to Washington. Here is Alan Bromley with President Bush and Yale President Bernard Schmidt. As Alan walked into the room in the White House, John Sununu, who was the chief of staff, he was a nuclear engineer from MIT, knew his stuff. John Sununu and the president asked Alan Bromley, what are to do with these people from Utah? They are promising to us endless energy. They want $25 million. What shall we do? Alan writes in his book, in his memoir of the scientist, fortunately, in my Yale laboratory, a group led by Moshe Gai, in cooperation with a group of Brookhaven electrochemists, had already shown that the Utah results were not I report to both the president and John Sununu, the chief of staff, with confidence. That's what the president wants. He wants to know up or down. I don't want to hear any detail. Should I give the money or not? All of this are done with one scoop, one signature, $25 million go out the window. Alan said, no. No, based on the experiment, he could speak with authority based on the experiment, or as Alan said, I can speak with confidence. No, this is not correct. As it turned out, I already told you on April 26th, there was a hearing in Congress where Pons and Fleischman were sitting there asking for $25 million. April 25, I get a call from Alan. He's already in Washington. April 21st, he went to Washington. You see how things are moved. I mean, it's like every day something new happened. April 25, I get a call from Alan and says, there is a hearing tomorrow in Congress. I need your paper. I'll tell you, I couldn't care about Congress. But when Alan tells me, I want your paper, Alan is going to get the paper. We only finished measuring on April 21st. 4 days later, he wants a paper. Sorry, 25, yeah. 4 days later, he wants a paper. So I send him April 26th. I don't have the time, but it was probably 4 o'clock in the morning. I say to Alan, I work with BNL people, Brookhaven National Lab, till about 4 a.m. Here's our paper. We worked it out by fax and phone. Of course, fax. This was a technology of the time. The internet was just in its. So, interestingly enough, on May 3rd, Pons and Fleischman fly from Utah to Washington to meet with President Bush. Imagine, this is now, they had a hearing on April 26th. They're going to meet with the president on May 4. May 3rd, they fly on May 4. And May 4, John Sununu, the chief of staff of the White House, canceled the meeting with Pons and Fleischman. Obviously, Alan is now in the White House. He's been in the White House for three weeks. He put a stop to this madness, sheer madness. What happened over here? Just a minute. Okay. How did I get myself into this project? At that time, I was an assistant professor at Yale, only about 6 years away from my PhD. My graduate student, Steve Rugari, and myself, we built a neutron detector. This is each one of these elements is a neutron detector. In the center, we have a pentagon, and the pentagon is surrounded by 5 truncated hexagons. This geometry is called truncated dodecahedra. Anyhow, 36 element. So 6 element times 6 makes 36 element, half of the sphere. 72 element close the sphere. You can surround your target with neutron detector. We have the state-of-the-art technology, data acquisition on a PC. Wow, you know, laptop were not available at that time, and we were just doing our work on with neutron detector for reason which you need not worry about. And lucky for me, everything that happened in cold fusion is in books. So all I have to do is open the book in the right page. On Thursday, March 23rd, 1989, around 6 p.m., I'm driving on I-95 North, exit 51, going back home from Yale to my home in Branford. And according to the book, I think it's a very correct description. I gave it to him. It must be correct. Moshe Gai, Yale nuclear physicist, remember he was on the expressway driving home when he heard the news on National Public Radio. I always listen to NPR. If it is true, it will be the scientific discovery of the century. Guy was fast approaching exit 51. There was barely time to maneuver into the exit lane. He crossed over the expressway, and let me tell you, rush hour, I crossed 3 lanes. I couldn't care less about the traffic behind me. I needed to go back to the lab. I re-entered in the other direction. I headed back to the university. I thought I knew how to check the Utah claim. From that moment, I spent 6 weeks in the lab. I was eating my breakfast, lunch, and dinner, sleeping on the couch. Sleeping. Who cared about sleeping? It was just the excitement. It was the excitement of the moment. I recall one time I didn't sleep for 3 days. What did I do? I went back to the lab and I says, aha. Remember those detector I just showed you? Those detector with the center pentagon and truncated hexagon. My idea was, let me flip one of these detector and let me put the cold fusion cell on top of this detector. If neutrons come from here, they will first hit this detector. Neutron mostly do they scatter. So I will have a neutron coming over here and scatter into the other detector. So here I will require the correct energy and the correct tail of a neutron, what we call pulse shape. So I know I have here a neutron with the right energy. Then I will determine over here the neutron with the right energy. And in addition, I will measure the time the neutron takes to travel from here to here, called time of flight. So I now measure the neutron 5 times over. Correct energy twice, correct pulse shape twice, and time of flight once. 5 times I determine that this must be a neutron. I overdetermine the event of interest and hopefully I remove the background, get a background free. So my idea was I test one pair. If that work, I call the student and said, let's go to work. So I worked all night, 8 o'clock in the morning. It became very clear that this I can do. I called the student and says, come on in, we have something to do. They all, with great excitement, started to work. Monday morning, I went to Alan Bromley and says, we worked over the weekend. We have the best neutron detector available in the country. I need electrochemists because I have no idea how to do the electrolysis. Alan Bromley made one phone call to Brookhaven. Next day, we started working on the experiment. So here is the experiment. This picture was taken after, in May, after we worked. Here is the experiment down here. Here is the cold fusion cell that were brought from Brookhaven. Here is our paper. Steve Rugari and Jiping Chow were the senior student. Ralph Franz became later a postdoc at UConn. He is now the chairman of the physics department in Georgia. Alison Davenport in Brookhaven, Hugh Isaacs from Brookhaven, and most important, Kelvin Lin, the director of material science department in Brookhaven. I became a very, very good friend of Kelvin Lin. This is one of the nice things that happened in cold fusion. I met some of the best scientists. Here's our paper published in Nature. Not only was it published in Nature, it actually became, what is this? Some over here, I already showed you that the paper, sorry, I already showed you that our paper in Nature was the cover page. So the cover story of Nature is our results. And here you see the place where we should see the neutron. In the background, after 8 hours, we measure 13 neutron. And when we turn on the cell, we even measure less neutron. So when we take the signal minus the background, we basically get 0 with an upper limit of about 1 counts per hour. Our rate was the best, 1 counts per hour, low background. Caltech was about 100 times higher. There was only one experiment there. Tunnel in the Alps, the Fréjus tunnel by the Bouget group. Okay, so now the country have to decide what are we going to do. They assembled the Energy Research Advisory Board panel. 21 members of this panel, some of the smartest people I've met, with the chairman is John Huizinga and Norman Ramsey. And they're now going from one lab to the other to see if there is any evidence for the. They were supposed to, Admiral Watkins required that they submit Admiral Watkins was the head of the Department of Energy, requested that they submit the recommendation by November. In November 2nd, I received a copy of the the recommendation of the panel. And something very strange happened. The panel met from July 15. I will tell you, there was a meeting in Los Alamos where they started. And Norman Ramsey and John Huizinga were co-chairing it. On October 31, 2 days before they submitted the recommendation, Norman Ramsey announced to the committee that he's resigning. And he said, by the way, I will rescind my resignation if you agree to put this preamble in front of the report. October 1989, Norman Ramsey announced to have the Nobel Prize. October 31st, he gives an ultimatum to the Energy Research Advisory Board panel. And he tells them, put this preamble over unless that I resign. He says, even the strongest proponents of cold fusion assert that the experiment, for unknown reasons, are not consistent and not reproducible at the present time. But Norman Ramsey said, but why? What if one of them is correct? A new standard for doing science. When I have not reproducible result, I sit down and I break my head and I find out what went wrong in my experiment. I don't submit it for publication, neither should you. But here we have a Nobel laureate giving an ultimatum. You have to say that this is still possibly correct after all that we have done. The most disturbing fact is that Utah did a control experiment. They did a electrolysis with normal water, no deuterium, H2O, not D2O. And their setup also have shown excess of heat with normal water. But normal water should give no excess of heat. This should be enough to anybody to say, enough is enough. It's complete nonsense. Let's stop this madness. Nevertheless, the report of the IRAP committee is still saying the panel also conclude that some observations attributed to cold fusion are not yet invalidated. What a slap in the face for 40 physicists who reported on May 4 in the American Physical Society our complete refutation of every measurement that was done. Norman Ramsey is pushing us to put this statement. Why? Because Julian Schwinger had an idea that cold fusion could be explained. But the panel said one more thing. The panel is sympathetic toward modest support for carefully focused cooperation. Cooperation? Cooperation between people that disagree? Have you ever seen two physicists that one says one thing and the other says, no, you're wrong? Usually they don't even talk to each other. And the panel says, we want to see cooperation. Why did they say that? There was a reason why they say that. And here's my last thought. On August 21st, 1989, Yale issues a press release. Scientists at Yale University, i.e. Moshe Gai, and Brigham University, i.e. Steve Jones, have agreed to collaborate on a research project to test recent results of cold fusion. The promoter of cold fusion and a skeptic agreed to collaborate. You may ask yourself, how did this happen? In July of 1989, I was invited to give a talk on cold fusion. I was told the conference will be broadcast on television. I was told to expect 1 million people to watch that. I've never given a talk to 1 million people. But you know what? I couldn't care less. What I cared is, in the front row of that conference, 21 people of the IRAP committee, some of the smartest people that I knew at that time, were sitting, and I had to speak in front of these 21 people. As it happened, on the way to the podium, I saw Steve Jones. We were very friendly, even though we disagree. We shook hands. Steve Jones is a Mormon, nice, believe in Christianity, very, very pleasant person, very humble. I shook his hand and I said, Steve, I think you and I should collaborate. And Steve, in a very shy voice, said, yeah, I think that's a good idea. Well, unbeknownst to him, I walk to the podium and I start my talk when I say, ladies and gentlemen, I have an announcement to make. Steve Jones and I have just agreed to collaborate. Oh, wow. Steve probably was very surprised. The Energy Review Advisory Board goes to Utah and say to Steve Jones, only one thing. When are you going to Yale to collaborate with Moshe Gai? Now Steve Jones, from this little side comment that he made to me, is now forced to collaborate. And perhaps this is the first time ever that two people that disagree agree to work in the same measurement. And there was a very interesting event that occurred in this measurement. Here, myself and Steve Rugari. Now you see our setup considerably more elaborate. We had more time to build fantastic shielding. And as we start the experiment, we're looking on display, and on the display we are writing 1 neutron detector fired, 2, 3, 4, 5. We have 12 detectors. And in the location of 1 neutron detector, we are getting a flood of neutron. The room is full of neutron. Steve Jones very pleasantly sits down back in his chair and said, I told you. Gary Taub, Steve Jones brought Gary Taub with him because Gary Taub was writing a book about cold fusion. Gary Taub walks in with a tape recorder, says, do you mind if I will now turn on the tape recorder? Go ahead. I mean, if we have a discovery, why not? Let's put it on tape. Meanwhile, I asked Steve, can you show me the data acquisition program that you wrote? He goes on, he printed, it's a 1-inch thick, 1 foot wide, perforated paper. I don't think you guys know about it. This is the old fashioned in which we had printout from computer. And we go line by line. I say, look, Steve, you are displaying the array from 1 to 12. But in the computer, your array starts at 0 to 12. Your array doesn't start at 1, start at 0. So what you tell me, 1 neutron fired, it's 0 neutron fired. Whoop. It changes, and of course there's no neutron. But meanwhile, all this drama happened. Steve Jones turning red, enormously embarrassed. All of this is on tape. Gary Taub is writing it. He told me at that point, up until that point when this occurred in your lab, I was going to write a book about Steve Jones, what a great scientist he is. Everything turned around. The book that I have shown to you, in fact, take direct target as the entire world into this embarrassing situation. But the story doesn't end over here. Now we want to publish our result. And as it turned out to be, I have just 2 more slides. In one of the talk that I gave, the 21 smart people, one of them, Dick Garwin, by the way, Dick Garwin was a student of Fermi. And Fermi said that Dick Garwin is the only true genius he met in his life. I completely agree. Dick Garwin is clearly the smartest person that I met in my life. For example, Dick Garwin was on a JFK assassination committee, the Warren Committee, and he came up with the idea that the microphone on the helmet of the policeman was stuck open, and one can do acoustic investigation. And if there was another shooting from the grassy knolls, and not all of it came from the book depository. Very, very smart. So in one of my talk, I made a mistake. Dick Garwin sent me an email, corrected me. So I said to Steve Jones, look, I want to publish the paper. We had collaborated. Says, no, we can't publish it. You have to do this and that and the other thing. Says, look, there is no perfect experiment. Okay, you can do many things, but we have done what we agreed to do. Let's just publish that what we have done under the circumstances that we measure, we found no neutron. No, we will not publish. Well, we have a problem. Collaborator doesn't agree to publish. I said, let's get Dick Garwin to be our arbitrator. After all, Dick Garwin already corrected a mistake I made. So he will be acceptable for you. We agreed. Dick Garwin wrote a legal memo sent to me by BitNet. You know, the internet didn't exist in 1990. BitNet was because it's their network. This was the state of the art at that time. And Richard Garwin is now writing an official legal document. Steve definitely and finally withdraw from the Yale experiment. And then he tells me, he's addressing it to me. So I hope you will go ahead with a responsible publication of the result. And interestingly, he signed, also an adjunct professor at Columbia University. He's an IBM TJ Watson fellow. And then he writes, views not necessarily those of IBM or Columbia, so legal. And he says, perfect experiments are not very common. Journal will be empty if we insist that all experiments are perfect. And says, Steve Jones should give you permission to publish. We published 1991. The first author is now Steve Gai. Myself and Calvin are at the end. And this was it. This was the last paper that we published. After that, we went back to do what we do and what we love to do, our nuclear physics science. And I think this is also the end of my talk. And I think I stayed within the time, right? Thank you.
Yes, absolutely. Yeah. Okay, I stop the recording. And dear students, because it's now out of time, yeah, if you would like, you may ask one very short question, so because we have 1 minute, yeah, and then other questions to Moshe. You send him emails, and you will contact by other means. Okay, do you have some questions, please? Yeah, we have a very brief question. Yeah.
Professor Guy, thank you very much for your talk. I'm just wondering if any changes have been made structurally to the scientific community